Hi there, welcome to lesson 3.2, part 2, how well the line fits the data. In the candy grab activity, we started with only one variable, the number of candies grabbed. To predict how many candies a randomly selected students would grab, we decided it would be easier if we used another variable to help us make that prediction, handspan, rather than just the mean number of candies. How much better will our predictions be if we use handspan to predict the number of candies rather than just the mean number of candies? We can answer this two ways, with s and with r squared. If we use the least squares line to predict the value of a response variable y from an explanatory variable x, the standard deviation of the residuals is given by s equals the summation of residuals squared over n minus 2 square rooted. So the summation of each of the observations minus the predicted value squared all over n minus 2. This value gives the approximate size of a typical prediction error, therefore how accurate the predictions are in terms of y. For the can tapping data, the standard deviation of the residuals is s equals 5.00 milliliters. Interpret this value. So we're going to interpret s just like we would a standard deviation. So it's the typical amount the data varies from the mean on average. Our predictions of soda remaining in the can based on the tapping time will typically be off by approximately 5.0 milliliters. The coefficient of determination is r squared. This is the percent of change in y that is explained by the regression line of y on x. R squared equals 1 minus the summation of the residuals squared over the summation of each of the y observations minus the y mean squared. You don't need to memorize this. An example. If we looked at a scatter plot of people's height versus weight and calculated r squared equals 70%, then we could interpret it this way. 70% of the variation in people's weight is accounted for by the linear regression line relating weight to height of people. Now that is one of those formulaic sentences that just has to be memorized, kind of like your interpretation of slope or your interpretation of standard deviation. Okay, it is formulaic. You have no freedoms here. No other explanation. Get in, get out, just this exact phrase. R percent of the variation in y is accounted for by the linear regression line relating y to x. An example, at a local pizza parlor, a large pizza is $8 with $1.50 for each additional topping. This is perfectly linear, so r equals 1 and r squared equals 1, or 100% of the variation in y is accounted for by the linear regression line relating y to x. Price is not, though, 100% based on toppings. The change in price is 100% based on the change in the number of toppings. So make sure that you don't skip any words because we would have a total different meaning. The pizza example, let's say that the parlor changes their policy to $8 for a large pizza, $2 for each meat topping, and $1 for each veggie topping. The following table shows the first few possibilities. So here's every one of the first few price possibility points, okay? 1 meat topping, so it's $2 more. Or 2 veggie toppings, so it's $2 more than 8. Or 2 toppings, 1 veggie, 1 meat, so now it's $3 more than 8. And here's just more and more possibilities. But these are the number of toppings total, and these are the prices total. Okay, so in other words, we start to have a graph that kind of looks like this. Yes, it's linear. It is not a perfect linear graph, though, anymore because of the variety of topping types and prices. Find r squared for the data above and interpret r squared. Okay, so I've put that data in my calculator in stat edit, and then I can go to stat calc linear regression option 8, L1, L2, and here it gives me the r squared. So r squared is 0.75. 75% of the variation in y is accounted for by the linear regression model relating y to x. So 75% of the variation in price is accounted for by the linear regression model relating price to number of toppings. Memorize this template for interpreting r squared then. Blank percent of the variation in y is accounted for by the linear regression model relating y to x. All right. So r is equal to the square root of r squared, but since r squared is always positive, then we have to be careful that we look at the direction of the pattern and ensure this pattern is going upward to the right. So r will also be positive, but remember that r is a correlation coefficient and that it talks about the strength of the linear relationship. R squared talks about the percent of variation in y that's accounted for by the linear regression model. That's all we can say about it, okay? But anyway, realizing what r's sign is up to you. So if we had a downward pattern to the right, and I just gave you r squared and I said determine what r is, you're going to take the square root of r squared, but you're also going to put a negative sign in front of it then. Okay, because it's a downward to the right pattern. So r squared and s both measure how well the regression line models the data, how much scatter there is from the least squares regression line. Remember that s is a standard deviation of the residuals, so that talks about the average amount by which the data varies from the linear regression line in terms of y variance. Okay, s measures the units of the y variable, while instead r squared has no units, it's a percent, and is on a standard scale therefore because it's out of 100. Neither address form or shape, so always look at the graph. You can't use r squared, or s alone to determine that a graph is really linear. Okay, when Mentos are dropped into a newly opened bottle of Diet Coke, carbon dioxide is released from the Diet Coke very rapidly, causing the Diet Coke to be expelled from the bottle. Will more Diet Coke be expelled when there's a larger number of Mentos dropped in the bottle? Two statistics students, Brittany and Allie, decided to find out. Using 16-ounce or 2-cup bottles of Diet Coke, they dropped either 2, 3, 4, or 5 Mentos into a randomly selected bottle, waited for the fizzing to die down, and measured the number of cups remaining in the bottle. Then they subtracted this measurement from the original amount in the bottle to calculate the amount of Diet Coke expelled. Okay, so they had x and y variables, the number of Mentos they put in the bottle, and the amount expelled, and they tried to control as much as they could, and they also used randomization. They tried not to choose all the Diet Cokes in a pack together. They tried to randomly select Diet Cokes at the grocery store. Okay, they should also randomly select their Mentos. They shouldn't choose all the first Mentos on the top of the packages. They should make sure that they open up all sorts of packages of Mentos, swirl them around a bit, and then make sure there's some sort of random selection process. Okay, so let's see here. All right, so we have a linear regression here, then we have a residual plot, and we have all sorts of information given to us, including s and r squared. For r squared adjusted, don't use that. R squared adjusted sometimes sounds like, oh great, it's adjusted, perfect, right? No, don't use it. Remember that this is the way that the linear regression equation is given to you in the AP Stats formula sheet. This is kind of the way that we see it in the calculator though. Remember that the constant's your y-intercept and the b is your slope. So constant is the a, then the other variable is your slope variable. So this is your a then, 1.00208, and this is your b, 0.07083. Okay, so what is the equation of least squares regression line? We have to be able to put that together ourselves. Y hat, the amount expelled, the predicted amount expelled, is equal to a plus bx. So constant 1.002 plus 0.0708 times the number of Mentos times x. Okay, define any variables you use. That's why I put the variables right in there in word form. Otherwise, if you do the letter y and the letter x, make sure that below there you say where y equals this and where x equals that. Okay, and you define them down there. All right. Okay. Interpret the slope of the least squares regression line. For every additional x Mento dropped into the soda bottle, the amount of soda expelled is predicted to increase by about 0.071 cups. What is the correlation? R equals plus or minus the square root of r squared. Since we only have r squared given to us though, not r, then we have to come up with the value of r. Now it is a positive graph, so we just need to square root it and leave our r positive. So we're going to square root 0.602 and get 77. So 0.77 is our r. Since the scatter plot increases from left to right, then r equals 0.7759. We keep it positive. Is a linear model appropriate for this data? And explain. Because there's no overall pattern in the residual plot and the scatter plot shows a clear linear form, the line is an appropriate model for the data. Would you be willing to use a linear model to predict the amount of Diet Coke expelled when 10 Mentos are used? Explain. No, because we don't know if the linear model continues past 5 Mentos. It's an example of extrapolation. Okay? Remember, you can't just say, no, this is extrapolation. You have to reason it out. It's good that you know the vocab word for this, okay? But you also need to give your reasoning, okay? Calculate and interpret the residual for a bottle of Diet Coke that has 2 Mentos and lost 1.25 cups of soda. Okay, so the 2 Mentos is an X and the soda lost is a Y. So the observed amount lost was 1.25 cups. The predicted amount lost was putting in a 2 into the prediction equation and getting 1.144. And if we go observed minus predicted, then we get 1.25 minus 1.144, and we get 0.106. A bottle with 2 Mentos dropped in it had about 0.106 more cups of soda expelled than expected. Okay, because observed minus predicted, there was actually more that actually got expelled than we predicted. Interpret the value of r squared and s. R squared, the coefficient of determination, goes like this. 60.2% of the variation in soda expelled is accounted for by the linear model relating soda expelled to the number of Mentos dropped in. S is the standard deviation of the residuals. It's 0.067. Using the number of Mentos dropped in the soda to predict the volume of soda expelled, our predictions will typically be off by 0.067 cups. If the amount expelled was measured in ounces instead of cups, how would the values of r squared and s be affected? And explain. R squared will remain the same because it is not measured in units of either variable. S is going to be multiplied by 8 because 1 cup is 8 ounces because the standard deviation of the residuals is measured in units of volume of soda expelled and the response variable y. Does it matter which variable x or y is x and which variable is y? For correlation, no. For the regression line, yes. Remember, b is equal to r times the change in s in terms of standard deviation of y over standard deviation of x. So switching y and x changes the slope. How can you calculate the equation of the least squares regression line using summary statistics? These are on the formula sheet. Note that the least squares regression line always goes through x bar mean, y bar mean. Okay, so b is equal to r times sy over sx. All right, and a is equal to y bar minus b x bar, which is just coming from this, a and b, and putting in y mean and x mean in for those, going to a and x mean, and making sure that you put y bar in for the a, because it's kind of like using y bar and x bar for an ordered pair, since your line goes through them. Okay, so that's where it's from y hat equals a plus bx. You can take that and you can switch it around and solve by subtracting a from both sides, subtracting y bar from both sides, y hat from both sides. Okay. All right, what happens to the predicted value of y for each increase of 1 standard deviation of x? Along the regression line, a change in 1 standard deviation of x corresponds to an r standard deviation of y. So that's what this means here. For each standard deviation of x, there's an r standard deviation of y change. So for an increase of 1 standard deviation of x, least squares of the line predicts it. Okay. So what that means is that that means that this dot is here to represent that this is where x bar mean and the y bar, so sorry, the x mean and the y mean cross, okay? Now, the regression line will always go through that. Now, as the regression line goes though, if r was equal to 0.994, then the regression line would climb up 0.994 of a standard deviation for the next, and it won't cross through one standard deviation of x and one standard deviation of y. It'll only cross to 99.4% of that mark, okay, in the y direction. So it'll be just less than a full standard deviation down for a whole standard deviation over. So it's saying that in a case where r is just 0.7759, like on page 14, then if for that relationship, the line would cross through x bar, y bar, but it won't cross through one standard deviation to the right and one standard deviation up. It will go over one standard deviation and it will go up 77% of the next standard deviation going upward. Okay, and then the same thing going downward. Okay, it won't cross through one standard deviation, or -1, -1. It'll only go 75% of the way, or 77% of the way. So what we're saying is for each standard deviation of x, we only cross through an r standard deviation of y. So what is regression to the mean? When the correlation isn't r equals 1 or -1, the predicted value of y is closer to the mean y bar than the value of x is to its x bar. This is called regression to the mean because the values of y regress to the mean y bar. The very first time the word regression was used in the title of this was in the title of this study, right here. Okay, a scatter plot of data of parents' heights and a scatter plot with their children's heights was compared. The parents' height scatter plot was constructed using a mean of the parents' height with a multiplier of 1.08 to the woman's height. Each offspring was compared to each of the offspring's parents' mean. It was found that two tall parents have offspring that are above average in height, but not as tall as their parents' height. Two short parents have offspring that are below average in height, but not as short as their parents' height. The offspring height regressed to the mean height y bar. The reference of regression is a biological reference of how second generations tend not to be as smart, as tall, or as extreme in general as their parents. More recently, a study was conducted on income. Based on a lot of data about parents' income and children's income, a parent making an income in the 10th percentile is predicted to have a child with an income in the 36th percentile, which is still below average, but is closer to the mean 50th percentile. A parent with an income in the 90th percentile is predicted to have a child with income in the 58th percentile. Their offspring is predicted to make above average income, but closer to the mean 50th percentile. The offspring income regresses to the mean income y bar. Putting it all together, regression and correlation. It does not matter which variable is x, or does it matter which variable is x and which variable is y? Not for correlation, but yes for regression, because slope has to do with change in y over change in x, so it also change your s, okay? The standard deviation of the residuals, because if you change which variable is y, then obviously the standard deviation of the residuals will change too, because the units are changing. Which of the following has the highest correlation? This is a fun graph sequence called Anscombe's quartet, and all of the correlations are 0.816. The exact same x bar and variance of x, and the exact same y bar and variance of y, and other factors that are really similar as well. Okay, in the meantime though, the moral of the story is plot the data before doing calculations. You can't look at r equals 0.816 and say, oh, it's pretty linear. Because yeah, you might be right. And then again, you might be off, okay? Correlation is just a supplement to a scatter plot. It is not the whole story. The least squares regression line is the same also. You can calculate a least squares regression line for this. Your calculator can take any set of 9 points or however many there are and calculate a least squares regression line for it, right? Just because it can do that doesn't mean that the points are actually linear. How do outliers affect the correlation, least squares regression line, the standard deviation of the residuals? Are all outliers influential? Correlation. If an outlier is in the linear pattern, the correlation increases, okay, for a positive slope, or decreases for a negative slope. Essentially, it means it gets closer to -1 or +1. So if an outlier is out here, and you have your scatter plot of points over here, then it's going to make your R closer to -1. Okay, if an outlier is outside the linear pattern, like here's your linear pattern going downward to the right, and you're going to pop it up to the right, R becomes closer to 0. The least squares regression line, the idea of springs for least squares regression line. Okay, so let's think of this. If you have an outlier in the x direction, it will pull the line toward it, making the slope positive or negative, increase or decrease. So let's say that you think of all these points here and consider all their residuals, and that you consider that this line right here is being pulled by springs, okay? And the spring is kind of pulling on the line, and that all these springs on the top and on the bottom have equal tension, placing that line right where it is, okay? Because all my positive residuals and all my negative residuals cancel out to 0 residual, because each positive value and each negative value, they zero out. Now, if you took one of those points though and you dragged it up further, it's going to take the line up with it. So if you took this point and you drag it way down, or if you make it appear way down here, then look at all that negative residual that you get. Your line slope is going to adjust, and it'll try to cancel out that negative residual, and it'll make all these positive residuals greater, okay? And it'll drag the line toward it. So outliers in the y direction, but closer to x bar, have less effect on the line as well, okay? So that means that if this point weren't so far to the right in the x direction, but we're closer to the x bar, then it won't have as much effect on the line, okay? Because remember that the line goes through x bar, y bar, okay? All right, standard deviation of the residuals. So what effect does an outlier have on that, on S? The further the outlier is in the y direction from the line, the larger S gets, because that's the standard deviation of the residuals. S means the typical amount the data varies from the line in the y direction. So if you make it vary a lot from the line, the S will get bigger. Are all outliers influential? A point is considered influential if removing it would markedly change the least squares regression line. So I would say that a point like this being introduced would be quite influential, because it's extreme in the x direction and it's extreme in the y direction. And anytime you have something that's many standard deviations out in both those dimensions, then you do get an influential point. Okay? Here is a scatter plot showing the cost in dollars and the battery life in hours for a sample of netbooks, small laptop computers. What effect do the two netbooks with the cost of $500 have on the equation of the least squares regression line? The correlation, the standard deviation of the residuals, and R squared. Explain. So what do these two dots have that affect it? Well, without these two dots, wouldn't you kind of see that the line would probably go up like this? But instead, with these two dots, which are influential, because they're extreme in the x direction and fairly extreme in the y direction, down here closer to 2, okay? So what effect do they have on this? The correlation, it decreases. It becomes closer to 0 and it is negative, okay? The regression line, the slope decreases, and the y-intercept, or A, increases because of the slope. Okay, decreasing, and it tips up the backside of the line. The standard deviation of the residuals, S, is higher. It's increased with these 2 points, okay, because they're further from the line. R squared decreases because we have a decreased percent of variation in battery life that is accounted for by the linear regression line with these 2 points. Here's a scatter plot showing the relationship between the number of fouls and the number of points scored for NBA players in the 2010-2011 season. So if they scored a lot of fouls, if they made a lot of fouls, did they also score a lot of points? Okay. Now there is a relationship that just says if you made a lot of fouls, that means you might be an aggressive player. It also means you might be on the court more. Okay. So people who get more court play tend to also make more baskets because those on the bench are not making baskets. But describe the association. The relationship between fouls and points scored is a moderately strong positive linear relationship with no clusters and no outliers. Notice that I didn't talk about the bench at all. I didn't talk about players, aggressiveness. I didn't talk about coach's preference, okay? Leave all that social stuff out of this and just get in and get out on what they're asking for. Describe the association, describe what you see. You want direction, form, strength, and outliers. Should NBA players commit more fouls if they want to score more points? Explain. No, because correlation does not imply causation. Playtime, where players get more opportunities to foul and score baskets, could explain why there is a positive linear trend. We see that players with more fouls tend to have more total points scored. Okay, so we consider that a confounding variable, which is a variable linked to the effect observed, okay? That we don't think that fouls are alone responsible for points scored. We don't think you can get out there and start slapping people's arms and just get more points then, okay? We think that points come from the baskets, so we think we want to introduce something else, like playtime, okay? And we want to talk about how it does the same thing that foul seems to be doing, okay? All right. Good luck with the lesson.